With this video, I would like to talk about some problems that deal with trig substitutions, which come from the table. Integrals that involve radicals such as a squared minus x squared, a squared plus x squared minus a squared, often can be solved by an appropriate trig substitution. The hint would be that there are no other methods that you know of that you could possibly use to solve the integral, and the only thing that would possibly work would be trig substitution. But I do want to remind you, there are problems that can be solved with more than one method. You could perhaps have a problem that has an integral with a radical that could be solved by trig substitution, but it also could be solved with another method of integration. My goal is just to teach you trig substitution. So I will try not to bring any other methods other than the trig substitution. The second half of this particular section, remember, section 8.4 in the new edition of the textbook, covers completing the square. So I'm going to start with some really basic problems first, and then I thought that we could get into some more complicated problems. I did a few of these in class, but obviously I did not have time to do a lot of examples. I want to remind you that during the class lecture, I worked the following example from your handout. So if you missed any part of this in class, here it is. And that's example number 1, and I know that I've given you the handout. And here's the completion, and here is the drawing of their rectangle. Then in class, we actually did the same problem again, but made it a definite integral. And we came up with a final numerical answer, which was exact. There we go. Square root of 3 minus 1 over 4. And I actually just found my new limits, and I stayed within my new limits. I did not go back to x. But if you wanted to go all the way back to x first before you did your fundamental theorem of calculus, just keep in mind that to go all the way back to x and use the original limits, you'd have to make that triangle so that you would know this. Or you could use your new limits and you could do the fundamental theorem of calculus here. And again, we did that in class. Regardless, if you have new limits and you stay in theta to perform fundamental theorem of calculus, or if you go all the way back to x and use the original limits, this is your final answer. Just be careful with the limits. That is where students make a lot of mistakes. The other problem that we talked about in class involved completing the square. And that problem is example 6. It says integrals that involve a quadratic expression where a is not 0 and b is not 0 can often be evaluated by first completing the square and then making an appropriate substitution, which could be just basic use substitution, by the way. It doesn't necessarily have to be a trig substitution, as you can see in this problem. I may or may not have had a chance to complete this problem in class. I know that the completion of the problem, we worked on completing the square on my quadratic x squared minus 4x plus 8. And remember, to do that, the term that you add and take away at the same time is going to be your term negative 4 divided by 2, which is b divided by 2, quantity squared. Negative 4 divided by 2 is a negative 2. Negative 2 quantity squared is a positive 4 that I added. That completes the square with the terms x squared minus 4x. Adding a 4 completes the square. Since I added a 4, I also had to subtract a 4 from this 8. C is equal to 8. And that gave us x minus 2 quantity squared plus 4. Talked about how when you would replace your quadratic with its equivalent, x minus 2 quantity squared plus 4, which is a sum of squares, that you could actually do u sub and let u be x minus 2. And then if you solve for x, x is equal to u plus 2. Break this into two indefinite integrals, u divided by u squared plus 4 and 1 divided by u squared plus 4. Here for this one, you could let w be u squared plus 4 and dw is 2u du. So you would need a 2 on the inside and a 1/2 on the outside, which they show here. And then therefore that's the 1/2 of natural log absolute value of u squared plus 4. Absolute value bars are not necessary because u squared is always positive, plus 4 is going to be positive. So they did drop the absolute value bars. Leave them if you don't know that you can drop them. And then they went all the way back to x, with x being x minus 2 squared plus 4. So there is the answer to the first indefinite integral when you decided to break it into two indefinite integrals. This one, if you go all the way back to your previous test, this is u squared plus a squared, and this is the formula for inverse tangent. Remember, it's 1 over a, inverse tangent of u over a. So that's 2 times 1 over a is 2, inverse tangent of u over 2, u over a plus c. And there's your final answer. So we did completion of the square. We did a regular u sub. We did not do a trig sub from the table. Other times we may complete the square and we may need to do a trig sub from the table. So there's all different kinds of problems. I'm going to show you more examples that are different from the ones that I showed you in class. I'm going to start off as a reminder with something kind of basic. I do believe this is also an example in the handout, but there's nothing wrong with doing an example that's in the handout. They also give the condition that x is greater than or equal to 5. I am not going to denote that condition here. I do want you to note that if I ask you to solve this by a trig substitution, it would be best to rewrite it like this. Then when you go to your table, you've got x squared minus a squared. So according to your table, x should be a secant theta. A secant theta. There are restrictions on theta such that you can get rid of this radical and basically end up with a tangent theta once you take the square root of a squared tangent squared. Off to the side, I'm going to say that x is a secant theta, which in this case specifically x is 5 secant theta. Then you need dx d theta, and that's 5 secant theta tangent theta. So dx is 5 secant theta tangent theta d theta. And I can go ahead and perhaps draw a triangle, but I'll wait on that and see if we actually need a triangle. We'll see. Let's go ahead and start the substitution process. Wherever I see 5, x, I'm going to put in 5 secant theta. So 5, I did it again, 5 secant theta minus 5 squared, all divided by 5 secant theta. Did it again. Must be tired. I apologize. Times dx, which is 5 secant. Did it right? Tangent theta d theta. My writing is so atrocious. I apologize. It's just really bad tonight. I apologize. Or today. The whole day. My handwriting has been terrible. Then, again, the whole purpose of the trig substitution is to get rid of the radical. So that's going to be 25 secant squared theta minus 25 all over 5 secant theta times 5 secant theta tangent theta d theta. Some students would go ahead and cancel the 5 secant theta with the 5 secant theta, and I think that's a good idea. I think we should do that. And then under the radical, we have 25 factored out, and we have secant squared theta minus 1. Our denominator now is 1 since I canceled with this 5 secant theta. And then we have to multiply by the remaining tangent theta there. I think you can see where this is going. This radical simplifies to the square root of 25 square root of tangent squared theta. Secant squared theta minus 1 is tangent squared theta, just like the table said and reminded us about. And then that's going to be 5. And that's going to be tangent theta times tangent theta. So the antiderivative of 5 tangent squared theta. And I do believe you should be excited. There's a famous blue box special for tangent squared. And if you're not excited, I am, because some of these problems are so difficult. It's nice to see that there's a formula to turn to. And the antiderivative of tangent squared is tangent x minus x plus c. So I'm going to use that. But remember, when I use this blue box special, I need to state it as tangent theta minus theta plus c. So be really careful. Tangent theta minus theta. And I'm going to be smart and say plus c on the overall outside. Now remember, our original problem started in x, and we've got to go back to x. Therefore, we have to think about, do we need that triangle? So we have 5 tangent theta minus theta, or 5 times the quantity of tangent theta minus theta, plus c. So the next step, I'll say 5 tangent theta minus 5 theta plus c. And we're going to have to go to another piece of paper, but I'm going to make my triangle. It comes from the fact that in the table we let x be a secant theta or 5 secant theta. Therefore, if you solve for secant theta, it's x divided by 5. And secant is 1 over cosine, or in terms of a triangle, secant is hypotenuse divided by adjacent. So my hypotenuse is x and my adjacent is 5. If you perform the fundamental theorem of calculus, the Pythagorean theorem, this opposite side is this radical. And again, prove that if you have to. that adjacent side a squared plus opposite side b squared is giving you hypotenuse side c squared. So 5 squared plus the square root of x squared minus 25 quantity squared equals x squared, hypotenuse squared. And then you can see that tangent is opposite over adjacent. So that's going to help us here. But theta we're going to express as inverse secant of x divided by 5. Excuse me. So final answer, we're going to say that according to our triangle, that's 5 times the tangent of theta. That's the square root of x squared minus 25 over 5. Minus 5 times inverse secant of x over 5 plus c. The 5's will cancel, and we will have the square root of x squared minus 25 minus 5 inverse secant of x divided by 5 plus c. Final answer for our original problem that looked like this. And before I forget to mention, there are some application problems throughout all of these sections, and I haven't really made you work on these, but the application problems involve, I know it's fun for you, it involves average value. They could ask you for arc length. They could ask you for surface area. So a lot of those things we did on test 1 and test 2 in terms of application problems, they could ask you a situation and ask you to find arc length. The deal is you'll use new methods of integration to solve an arc length problem now, or new methods of integration to solve a surface area problem, new methods of integration to solve, I don't know, volume by disc washers. I don't focus on those too much, but just do please know that you can always have these problems, and when you go to set them up, you need to use these new methods of integration, like integration by parts, trig integrals, trig substitution, and finally partial fraction decomposition. So the final answer is the square root of x squared minus 25 minus 5 inverse secant of x over 5 plus c. That was a very, very basic example like the one I did in class. And again, it was also in your handout. I'll put that on the document camera and show you before we move to something more complicated. It was actually example, oh great, example number 4, by the way, in the handout is an arc length problem. And it involves, when you plug into the arc length formula, you have to do the concept of a trig substitution from the table. Beautiful, beautiful example. Again, I don't focus on those too much. So the problem that I just worked for you is this one. I guess you would say that is example number 5. It's at the bottom of the page, and it goes over to this page. And you can see the triangle, and you can see all the work. And you can see your final answer. Very, very basic example. Okay, now it's time to leave the handout and show you another example or two of other perhaps trig substitution problems, or perhaps completing the square problems. I'm going to show you this one because it doesn't fit into the norm. To be honest, on a test, I would probably say use a trig substitution from the table to solve this problem. Most students would say, I don't see a radical, so why would I use trig substitution? But you can technically use the table, even though it states radicals, a squared minus x squared. We could technically still use the trig substitution table to solve something like this. So what we have to do is we have to think about looking at the table and our difference of squares. It is a squared minus x squared, even though it's not under a radical, it's inside parentheses, 1 squared minus x squared. So x is a sine theta. So I'm going to write that off to the side. And in this case, a is 1, so x is sine theta. And then dx is cosine theta d theta. And we need all of this. And a is 1. I'll do that here. We also will have new limits. It's easy to find the new limits because according to what our table said, theta is going to be inverse sine of x. So if x is 0, then theta is inverse sine of 0, which is 0. And if x is a half, then theta is inverse sine of a half. And that's going to be 30 degrees or pi over 6 for the new limits. So here we go. In place of dx, I'm going to put cosine theta d theta. In place of x, I'm going to put x is sine theta. So remember, that's 1 minus x squared and then quantity squared. So that is very important. Then I simplify because I want to make sure that I work this out to an integral that I can deal with. If you wish, you could just put the d theta out here now, but leave the cosine theta in the top, or you could multiply by cosine theta that's in the numerator. I'm going to say that this is 1 minus sine squared theta, but then remember to square it again. 1 minus sine squared theta is cosine squared theta. I see where it's going. I hope you do. And then cosine squared theta quantity squared is cosine to the 4th power. The cosines, well, one of them cancels. And that leaves you with 1 divided by cosine cubed. And then cosine cubed, 1 divided by cosine cubed, is secant cubed. I mean, I don't like that, but there is a blue box formula for it. Secant cubed, you don't have to plug into the reduction formula and prove it. So take out your formula sheet and locate the blue box special for it. And again, we're going to have to think about this in terms of theta, though. 1/2 secant theta tangent theta plus 1/2 natural log absolute value of secant theta plus tangent theta plus c as the blue box special in terms of theta with my new limits. Usually I would write that down, but to save time, just know I'm referencing this particular blue box special. And I know that's going to be relatively long, so I am going to write 1/2 secant theta tangent theta plus 1/2 natural log absolute value of secant theta plus tangent theta. And I'm going to do brackets from 0 to pi over 6. So inside the brackets would be my blue box special for secant cubed. So then the hard part is substituting in pi over 6 and then substituting in, I love the limit of 0. And that's going to take a little bit of algebra. And then we'll arrive at our final exact answer. So 1/2 secant of pi over 6 tangent of pi over 6 plus 1/2 natural log absolute value of secant pi over 6 plus tangent of pi over 6. Because of space, I'm going to say minus 1/2 secant of 0 tangent of 0 plus 1/2 natural log absolute value of secant 0 plus tangent 0. There we go. And you could put it into your calculator, but I'm going to quickly show you at pi over 6, cosine is the square root of 3 over 2. Sine is 1/2. At 0, cosine is 1 and sine is 0. So 0 radians, or 0 degrees, 30 degrees, pi over 6 radians. All we have to do is worry about secant and tangent of those angles. So secant of pi over 6 is 1 divided by the cosine of pi over 6, which is 1 divided by the square root of 3 over 2, which is 1 times 2 over the square root of 3, which is 2 over the square root of 3 times square root of 3 over square root of 3, which is 2 square roots of 3 over 3. So we'll use that. And then tangent of pi over 6 is equal to the sine of pi over 6 divided by the cosine of pi over 6. Sine of pi over 6 is 1/2. Cosine of pi over 6 is the square root of 3 over 2. 1/2 times 2 over the square root of 3. 1 over the square root of 3 times square root of 3 over square root of 3 is square root of 3 over 3. Okay, that helped me there. And then, and I just noticed something. That's supposed to be 0. I made that a theta, but I'm substituting in 0. Secant of 0 is 1 over cosine of 0, which is 1. But see, tangent of 0 is sine of 0 over cosine of 0. Sine of 0 is 0. Cosine of 0 is 1. So 0 over 1 is 0. This is going to 0. This is not. Secant of 0 is 1. Tangent of 0 is 0. So this is going to go to 1/2 natural log absolute value of 1. Natural log of 1 is 0. So I would say, all in all, when we substitute 0 in, all of that entire expression goes to 0. So I'm just going to worry about saying 1/2 times the secant of pi over 6 times the tangent of pi over 6 plus 1/2 natural log secant of pi over 6, which is, let me do this. It's just too messy. I apologize. Let me come back here. So 1/2 secant of pi over 6 is 2 square roots of 3 over 3 times the tangent of pi over 6 plus 1/2 natural log absolute value of secant pi over 6 plus the tangent of pi over 6. And then the rest of that, all of that, I'll just say minus a big super big 0. So all of that is 0. So over here, we've got to continue with our algebra. You can see your 2's cancel. Square root of 3 times the square root of 3 is 3. And 3 times 3 is what? 9. Plus 1/2 natural log absolute value of 2 square roots of 3 plus the square root of 3 over 3. 3/9 becomes 1/3 plus 1/2. A lot of students would not think about this, but 2 square roots of 3 plus an understood 1 square root of 3 is 3 square roots of 3 all divided by 3. The 3's cancel. So 1/3 plus 1/2 natural log absolute value of square root of 3. It depends on the solution manual, but I will say that I have noticed that they don't condense this natural log. They actually expand it because they say that that's the natural log of 3 to the 1/2 power. You don't need the absolute value bars. And then this 1/2, they actually bring it in front and make it 1/4. So I could ask you for a single quotient where the denominator is 12. I could let you leave it this way. And I suppose some people may express it as 1/3 plus the natural log of 3. Guess the 4th root of 3. But this is the way they gave this particular problem in the solution manual. And that's your final exact answer for that one. So that one was kind of neat. It did not involve a radical, but we were still able to use the trig substitution table to reduce it down to something we could work with. So I wanted you to know that it's not always got to be a radical to be able to use that particular table. Okay. I think that we could complete the square on 1, and I really think that would probably be a good place to stop the video. We did a really basic completion of the square in class. So I'm going to do a problem where the coefficient for A is not originally 1. So let's see what that's going to look like. And then I'll conclude this video. I don't want to give you too much at one time. Obviously, there are going to be many more examples of trig sub that I can show you. But with this one, I would say in directions, solve by completing the square in the denominator. And I may give you a workbox to work on that denominator completing the square. A is 4, B is 4, and C is 5. To be able to complete the square on the first two terms, A has to be 1 to complete the square. If A is not 1, you cannot complete the square. So with the first two terms, you can factor out a 4. And it's the x squared plus x that I'm going to complete the square on. And if I'm completing the square on x squared plus x, a is now 1 and b is now 1. So we're going to say 4 times x squared plus x plus some other term plus 5. And whatever we put in here, we got to take and get rid of it at the same time. How do we determine what's inside? To complete the square, it's b over 2 quantity squared. So in this case, it's 1 over 2 quantity squared, which is 1/4. So I add a 1/4 inside. At this point, I've changed the complete expression. Here it's the same quadratic I started with, but when I add this 1/4 to the inside to complete this square, I've changed the problem. So we've got to get rid of what I put in there. And the trick is, I should not say minus 1/4 here like you would think. I've actually put 4 times 1/4 is 1. There you go. Get rid of the 1. You actually put a 1 in the original expression. So take and get rid of it at the same time. Then this can be rewritten as 4 times some quantity squared plus 4. And that quantity is x plus a half. So x plus a half times x plus a half is my perfect square trinomial, x squared plus x plus 1/4, if you FOIL this out. Where do I get the 1/2 from? How do I find my binomial? b divided by 2 before you actually square it is always going to help you with that binomial, and that was a positive 1/2. So x plus a half quantity squared will give me this perfect square trinomial. Then, that's the hard part. You got to come back and you've got to rewrite the problem and make this 4 times x plus a half quantity squared plus 4. Okay? And then you could think about things you could do. Technically, I could write my denominator as a sum of squares. This would be 2 times x plus a half quantity squared plus 2 squared. You would not want to FOIL everything out because you just get back to where you came from. And this is a rational expression, so long division's not working. The degree of the numerator is 1, the degree of the denominator is 2. So we had no choice but to complete the square. We have to think about if we could actually use the trig substitution table, and there may be a way, but before we could do that, we would have to be able to probably do a couple of rounds of U sub. So I would suggest that we start by letting U be x plus a half. And then du equals dx. You'll also want to solve for x. X is u minus a half. So you're ready to substitute in. 2 times u minus a half plus 3 divided by 4u squared plus 4. And in place of dx, put du. So 2 times x, x is u minus a half plus 3 divided by 4u squared plus 4. You can distribute the 2 to the u minus 1/2. That'll help. So 2u minus 1 plus 3. Okay. 2u minus 1 plus 3 is going to be 2u plus 2. I know you're thinking that the denominator could be written as 2u quantity squared plus 2 squared, and you have a sum of squares. And if you're thinking that you would maybe use the trig substitution table you would have to let W be 2U and DW be 2DU. So we would need a 2 on the inside and a 1/2 on the outside. This is another problem where in the numerator you'd have to solve for U, which is W divided by 2. Now I've not worked it that way to see if we could perhaps still use the trig table. You may want to try that on your own, trig substitution table. But the way that I did it is I noticed that the numerator has a 2 in common and the denominator has a 4. So I made life easy and factored out that 2/4. So that should help. You may not see that, but you will break this up into 2 indefinite integrals. The first one is 1/2 times u over u squared plus 1. And the next one is also 1/2 times 1 over u squared plus 1. For this one, if you go back to your inverse trig integrals, you will see that 1 divided by a squared plus u squared, sorry for the connection and the disconnection, apologize, is equal to inverse tangent. With this one, I'm going to do u sub. So I'm going to take 2 different approaches here. Okay. I'm going to cross this out. Here we go. Let W be u squared plus 1, so dW is 2u du. I'm going to take my purple pen, and I'm going to put a 2 here and a 1/2 outside here. So I'll say this one is 1/4, 1 over W dW. This one is going to be basically my inverse tangent formula with A equal to 1. And so this is 1/2 times 1 over 1 inverse tangent of u over 1 plus c. Again, you may be saying, Miss Manhart, you're not supposed to have a w and a u in the same step. You're not supposed to have a w and a u in the same integrand. But this is an integrand I've already integrated here. That's why you see a w and a u. But within the same integrand, any one of these, you cannot have a u and a w in the integrand at the same time. So this one involved a round of u sub. This one involved looking at your inverse tangent formula. Then I know that I got to go all the way back to x regardless. So for this one, you can rewrite it as 1/4 and find its antiderivative, which by formula is 1/4 natural log absolute value of w plus 1/2 inverse tangent of u plus c. And I'll start by thinking about w was u squared plus 1. Now we have a step where they're both in U, and U was x plus a half. Some people will leave the final answer this way, and I'm fine with it. 1/4 natural log absolute value of x plus a half quantity squared plus 1 plus a half inverse tangent of x plus a half plus c. I'm also okay with if you decide to drop the absolute value bars, because it's x plus a half quantity squared, which is always positive. Add a 1 to it, and that's always positive. If you don't know that you can drop the absolute value bars, though, you better leave them in there. Now, some people will FOIL all of this out and collect like terms. So I'll say this is okay. This is okay also. I just don't recommend it. So they FOILed x plus 1/2 out and times, well, x plus a half times x plus a half. And then they added 1 to it. And that's what you basically end up with. I kind of like the way this one looks compared to this one. I can't tell you which one the textbook prefers, because there are times when you'll see that they leave it like this. There are times when you will see that they leave it in this form. So I can't really tell you which way they decided to go with that. I hope that has been helpful. So either one of those would be okay. If I didn't want you to go this far, I would say in your final answer, there's no need to, I don't know. I guess I'd have to say there's no need to simplify the quadratic here when you're dealing with natural log in the final answer. There would be no need to full it out and simplify that quadratic into 3 separate terms. Or I may just leave it open, and either one would be acceptable. So this is going to conclude the video on trig substitutions and also solving integrals by completing the square. Most students find that they need to practice completing the square problems compared to the trig substitutions. So it's because I think it's been a while since people have actually worked on completing the square. And also, when you did work on completing the square, it involved more or less like a quadratic equation. 4x squared plus 4x plus 5 equals 0. And you were completing the square on the quadratic equation so that you could solve for x. But here, we're not completing the square on a quadratic equation. We are completing the square on a quadratic expression. Big difference. Similar, but different. Bottom line, you cannot change that quadratic expression. So when you go to rewrite it and complete that quadratic expression, what you end up with, which we went from original problem or denominator to here, this, if you multiply everything out, will give you the 4x squared plus 4x plus 5 back. It better, or you did not complete the square correctly. I will actually recommend that if you think that you have successfully completed the square on something this difficult, I would highly recommend that before you start working the problem any further, that you FOIL all of this out and make sure that they are equivalent. Because if they're not, and you made a mistake in completing the square, that means you made a mistake from the very beginning of the problem, and you're never going to get the right answer, unfortunately. So when you can check something out like this, it takes a little, bit of time. When you can check it out and make sure you get the original one back, why not take that extra moment instead of constantly getting things wrong when this was the problem the whole time. And you could spend hours and hours on getting this wrong, or trying to prove what went wrong, where you could just go ahead and say, well, it can't be this because I foiled everything out and I got my original quadratic. So I hope you have a good day, good night, good morning, and I will provide my next video on partial fraction decomposition. I actually have a few problems that I typed up. If you remember the handout that I gave on my very first lecture video dealing with trig integrals, I did these 3 problems on my very first video. I actually extended this particular handout to incorporate trig substitutions like you see here. Number 6 and number 7, and I believe number 8 would be the third video or fourth video, partial fraction decomposition. So what I thought I would do in my next video, before I start the lecture on partial fraction decomposition, I thought that we could do 4 and 5 trig substitutions as a review. Get the answers and then move on to the lecture on partial fraction decomposition. So stay tuned. Again, if you'd like this hard copy of this document, starting from the very beginning, the very first video, and now I've added a couple more problems from the chapter, just send me an email and I can attach this. I don't have it all worked out, but I can attach it and give you the final answers. D, D, B, A, C, A, B, and A. But hopefully we will be able to work problems 4 through 8 together on the next video. God bless you all.